Let's get started. So thank you all for being here to this ELLIS Distinguished Lecture. It's my pleasure to introduce Rico Sennrich, who's an associate professor at the University of Zurich, both affiliated with computer linguistics and computer science, as I just learned. His research is on natural language processing, in particular machine translation, and also how to do this with low research languages. And I think this is also the topic we will hear more about today. He's known for many things, but one of the most impactful pieces of his work is about how to use sub-tokenizations or sub-word tokenization in machine translation. So some of you may have seen this paper at some point. He is currently in Zurich. Before that, he also was affiliated with the University of Edinburgh. And even before that, he did his PhD and master, I think, in Zurich as well. He's also an ELLIS fellow and involved in various roles in the NLP community. And it's a great pleasure to have him here today. And I leave the stage to you.
Thank you, Michael, for this nice introduction, and thank you for the invitation. Like Michael said, I'm going to be talking about low-resource natural language processing. And the title says I'm going from the very beginning, from tokenization to the very end, from inference. Small spoiler, I'm going to skip everything in between. So it's just going to be tokenization and inference. And I'm going to start a few years back. This is a picture Mirella Lapata made at a talk in 2017, where she's channeling the scream. And this was in reaction to neural networks taking over the field and being so effective. And she's asking is natural language processing now dead? Do we still need our domain knowledge, or is it just all neural networks? Of course, Mirella at the time said the answer is no, natural language processing is not dead, but also, as we know in the years since, that quite a few task-specific methods have disappeared and have been replaced by these more general methods, neural networks, large language models, which have shown to be very effective. And I'm telling here the bitter lesson that's actually from a blog post by Richard Sutton, where he says the same thing, general methods that make scale with compute often outperform some methods that try to make use of our human knowledge of the domain. So talking about low-resource NLP, we can ask us the same question. Is this still something where we can use our knowledge to tackle this challenge, or is this just a data problem? Do we just scale things up, collect more data from these small languages, and then we should solve natural language processing for them automatically? And you can probably guess my talk today is about that the answer to this is no, that we can still make use of our knowledge of models, knowledge of languages to make things better. And I also want to make the point that if you just scale everything up, you might increase the absolute amount of data you have for many languages, but relatively speaking, you will still have an imbalance, and maybe this can be represented here well with Llama 2 models, which are 90% trained on English data, and then there's this 8% unknown data. That's actually not unknown, that's just things that aren't languages, computer code, Python, C++, whatever. And then the next biggest language in the Llama 2 mix was German, with 0.17% of the data. It's still impressive that these models are then still have some multilingual capabilities, despite this low proportion of data in other languages. But of course, these are just the top 20. And as you go to higher in the list of these estimated around 6,000 languages in the world, you will have tinier and tinier fraction of data, and you can't just increase the proportion of all of them at will. Here's, by the way, an overview of the number of speakers per language, which is still the top 30 languages, so are half the speakers of the world. But it's more evenly distributed than what we have in terms of resource availability and accessibility, which is more tilted. So there's a big demand to make these language models more multilingual, also not just from a commercial point of view, but also from a point of view of equity and inclusivity, especially if you think about language models being a tool that can empower you, that can give you access to information, that can improve your productivity. If you only have this support tool for some languages but not for others, this causes inequity. So what are some of the problems we face now? And starting at tokenization, this is from Luke Sedelmayer's talk at ACL last year in Vienna, where he talks about the fairness issue of byte-pair encoding tokenization. So byte-pair encoding is this subvert strategy where we don't operate on the character level, not on the word level, but somewhere in between. Quite a good compromise between actually being like at the same time open vocabulary, at the other on the other side more efficient than being purely on the level of characters or bytes. And it's a method that's widely used in large language models, but then it has this problem of being data-driven. And if the data is dominated by English, that also means that the compression that is learned in byte-pair encoding favors English, and other languages like here Tibetan, you actually get much longer sequences for the same message that you get for the message in English. Why is this a problem? Well, if you pay on an API per token, that means that actually processing Tibetan is 10 times more expensive than processing English if you're talking about the same amount of text that you put in. So there's a clear monetary unfairness in this tokenization. There's also questions about the effect on quality of this. I won't go into the quality question too much now, just purely the economic inequities. Reason enough that we say we actually want to have more fairness in the tokenization. Andrei Karpathy had a quite popular series of tweets and a video explaining tokenization, and actually talks about that a lot of the weirdness in large language models is because of tokenization, specifically byte-pair encoding tokenization. I won't go into all these points, but yeah, you can also see the unfairness across languages here being mentioned. He concludes that tokenization is the real root of suffering. As the person bringing byte-pair encoding to tokenization, I'm not sure if I should feel honored or upset that apparently this is now the real root of suffering. But yeah, let's try to do something about this, at least about this third point here. So tokenization is data-driven, so you could say, okay, just balancing the training data, that should be enough to actually get fairness here. But it turns out that it's actually more complicated. There are, on the one hand, there's linguistic properties that play a role here. So if you just have the same amount of data in English and German, I love you, you love me, ich liebe dich, du liebst mich, you can see that love now is more frequent than Liebe and liebst, just because of the morphology of the languages. Then we train a multilingual tokenization where we have like a shared tokenizer across many languages. So imagine your language mix is now English, German, Spanish, French, and Greek, and you can see that actually some of the strings are shared here. The rich is shared across 4 of the 5 languages, with Greek then being an outlier. So that means that even if you balance the training data, then Greek will still be processed less efficiently, will be at a disadvantage compared to like Latin script languages. So just balancing the data doesn't really work. That's also like a philosophical question. What does balancing the data actually mean across languages? Because then you need to answer the question, what is a language? And we know this from things happening in Switzerland. So we have 4 national languages, and the 4th one, Romansh, the smallest one with around 50,000 speakers, they have a kind of like, there's Romansh Grishun, which is like a constructed language, a compromised language between the different dialects called idioms in Romansh, but it's not widely accepted by the community, and the community actually wants to have a better official recognition of the different variants of Romansh, like Sursilvan, Surmiran, Sutsilvan, Puter, and Valader. They're also saying like these variants actually so different from each other at times that they're not mutually intelligible if you haven't been trained on the other variants. But still you can see some similarities, like this Funcionesca here appearing across different variants. So if we now say we balance our training data to have the equal amount of data by language, if Romansh now goes from 1 language code to 5 language codes, does that mean we are increasing the amount of Romansh training data, and will this also lead to unfairness in the tokenization? So before we go to the solution we propose, let's talk about the question whether maybe subvert segmentation, maybe tokenization is to blame. Like Andrei Karpathy says, it's the real root of suffering. But I want to actually make the argument tokenization is also part of the solution, because what other choices do we have? Well, we could go to the character level, but then we have the unfairness between alphabetic writing systems and logographic writing systems, where the same message in English, like Zurich, is 6 characters. In Chinese, it's here 3 characters. We have syllabaric writing systems and in between. So this will not be fair in terms of just pure length of a message. We could go to the byte level. If you do UTF-32, that's just 4 bytes per character. That has the same problem as the character level. UTF-8 also has unfairness encoded in it, in that actually it's like a compromise that tries to be most efficient for Latin script, and it's just Latin is just 1 byte per character, and then other scripts are like 2 or 3 bytes per character. So you can see here with Chinese 3, Greek 2, Thai 3 bytes per character, you get unfairness on that side. So I had a picture of Luke Settlemyer up earlier. He actually was talking about the problem of fairness in byte-pair encoding, and one of the solutions they propose is byte-level models, but not purely byte-level models, but actually byte-level models that internally do some compression, because you have to do some compression to actually reach the same efficiency as the subvert models. Unfortunately, they don't really talk about the fairness aspect in their paper, and it was a bit weird to then have like as motivation this unfairness of subvert segmentation and then not actually discuss the solution. I do think the work is very interesting, but I want to say a bit more about why byte-level models don't automatically solve fairness, and this also has to do with like how do we actually encode, how is UTF-8 actually encoded. And if you look here, you see that you have this ASCII block, like all the Latin characters being 1 byte, and then the 2 or 3 byte characters, they will have a character from one of these blocks, which indicate that this is the first byte of a 2 or 3 or 4 byte sequence, and then you have these continuation bytes that then fill up this code block. And for example, if you take Arabic, every Arabic character will start with one of these 2 bytes and then continue with these continuation bytes. Now, this byte latent transformer actually uses entropy as a measure, as a way of segmenting the sequence into patches for compression. And the entropy idea is, well, it actually makes kind of sense for English. As you say, oh, when the entropy goes up, this is usually like at the beginning of a word where you have the most uncertainty, and then you start a new patch, but you might have things like names, Daenerys Targaryen or George R.R. Martin, like multi-word units that actually have a very low entropy, because once you start with the name, it's very clearly that you're going to continue with that name, so you can have this as one patch. So it works quite elegantly on English to have this idea that entropy can be a signal for starting a new patch. Of course, if you then do this multilingually, the question is, will the entropy be the same across languages? And that's probably also going to be a data problem, that if your data is not balanced, no, it won't be the same. There's also then interaction with the number of bytes you have per character, because if the same message has more bytes, the entropy per byte will also be different. But it also interplays with UTF-8 encoding, because if you actually have every character in Arabic start with like 1 out of 2 choices, once you're ending a character, you have a very low entropy, and you know, oh, I'm going to have one of these starting characters again, and then the entropy spikes because the continuation characters, there's many possibilities. So you have this zigzag up and down in the entropy. So the idea of, oh, we can start a new byte, for example, when the entropy increases, like you look at the monotonicity, works nicely in English, but doesn't really work in Arabic. To say, oh, let's have some global threshold whenever the entropy of the next character is above some threshold, also works in English. A bit less clear how it works across other languages. So Dominic Fisher, a master student, has been looking at this and also showed with the model that Meta has trained their entropy model on, there is a premium like in parity between English, which is here at 1, and other languages, which are like up to 11 times more patches than English. So if you have imbalanced data, this doesn't automatically improve fairness. So okay, enough criticizing other methods. What do we propose? Well, this is work that we will present at ACL next month by Nega Clara, and others. And Debje, Joel, Sina, Antoine, so now I have all the names. The core idea is that we can actually make this part of our objective when we train the tokenizer. So this is nice because we don't need to care about balancing the amount of training data per language. We don't need to care about these interactions across languages, that we have a cluster of very similar languages that somehow help each other out and improve the statistics, and then this becomes more efficiently compressed, where the outlier languages like Greek are less efficient. If we make it part of our objective when we train a tokenizer, we can actually compensate for all of these problems. And it turns out it's actually a very small change to the byte-pair encoding algorithm. So if you're not familiar with it, in byte-pair encoding you kind of have a few things that you need to define beforehand. The vocabulary size you want to reach, you have to give it a training corpus, and you need to decide what is your initial vocabulary. Typically this is like character segmentation or byte segmentation. You also define like which merges do you not allow. Typically you don't allow merges like between Latin characters and punctuation or across space symbols. This is what we call the pre-tokenization nowadays. And then once you have that, you actually just start counting. You count for every pair of symbols, or here characters are bytes in the beginning, but then subwords become also symbols that can be merged in the future. You count the frequency, you find the most frequent pair, and you merge it together. And then you recalculate all the frequencies to find the next frequent pair. And you can do that in a loop until you reach the vocabulary size that you want. So parity-aware byte-pair encoding, it's very similar, with the difference that we actually now need language information in the training corpus. So we have now one training corpus per language. I think that's fine because if you want to do something like rebalancing training data, you do language identification anyway. And then we use a development set that we say this is a multi-parallel development set like Flores, which we use to say, oh, these are translations of each other, so it's the same message. So the length of this development corpus in terms of the number of tokens you have after tokenization should be the same across languages. And to enforce that during training, we can now actually, we calculate the frequency now separately for each language. And then instead just picking the most frequent merge overall, we are first deciding which language is the worst compressed now, which language has the most tokens in our development set. And this is going to be the language which we pick for the next merge. And then, yeah, we find the most frequent symbol pair in that language. And then, importantly, we update the statistics in all the languages. So that's what makes us different from just saying, oh, we train a bunch of monolingual tokenizers and then combine them in some way. In that a merge from one language also is accounted in the other languages for seeing, like, what are the statistics, which is the best merge. And then everything else is the same. We keep doing that until we reach our vocabulary size. Just to hammer this point home, why this matters that the frequencies interact with each other. Imagine you have monolingual tokenizers. In one language, you now have already decided, oh, I'm going to use the merges from that language. I'm merging A and T to et, and I'm merging M and et to mat. And now in another language, you have these possible merges. You have a merge that says, oh, I can merge R and A to ra. We can still allow this. This is fine. It's not conflicting with what we have before. But it might not be as efficient as it was if we didn't have A and T merged to et, because every occurrence of ret we will no longer count as occurrences of R and A, because A has already been merged together with T. And then there might be merges like R and A becomes ret. Ra and T becomes ret. This one we will no longer allow because this is actually completely blocked. We will never see Ra and T in our corpus after A and T have already been merged to et. So these are the interactions between languages that we can actually take into account to make this more efficient. Yeah, quite a simple algorithm. Let's already look at some results. I can see people are getting hot. So it seems to work quite nicely. So this is the original byte-pair encoding. This is now over 30 languages, vocabulary size 128. We take the FineWeb 2 corpus without doing any balancing of languages. And then we have the Flores development set for as a development set when we train the tokenizer, and the results I show you are with the dev test. And it seems to be almost perfectly fair, except English is a bit better. I think that's just because there's like English text fragments in the training corpus of the other languages. But I think that's also fine because people care about efficiency for English, because English is used a lot on the web. So maybe you actually you don't want to lose too much efficiency for English. Maybe I think this is maybe around 25%. I mean, you can't get a free lunch, right? If you reserve some some merges for some small languages, you can do less merges for English, and you will lose some efficiency for English. And maybe you don't want to have like this 25% penalty for English. So we looked at some variants of that, where we say, for example, we can do something like a hybrid strategy. We can do the standard byte-pair encoding based on like the global frequencies dominated by English for like half of the steps is what we did, and then do the parity optimization only for the second half of the step. And we still get good parity here, except that English is now more efficient than the others, but that's actually also intentional. And this is also a strategy if you care about something like Python code, like I know Michael does. There's no way that you can have like a parallel data set to say, oh, I have now an English text, and I mean, there might be some special areas where you can do that, but not generally that you have some English text and then you have the equivalent Python code. So how do you define parity there? You can't really, but here with this hybrid method, at least you have a way of still saying, oh, I can still add programming data into the algorithm, and it will still be considered in the first phase. There are some weird things happening that if you do pre-tokenization and you say, okay, I'm not gonna allow merges across space, then you have languages like Chinese where they don't use the space characters, and they could be merged could be made more and more compressed if you increase vocabulary size. But other languages that actually use like lots of small words, eventually you reach the point where even if you keep merging in that language, you will not improve the length on the development set. You kind of get stuck with the algorithm, you kind of get stuck in that language. And that's not something we want. So we actually also looked at something where we say, okay, let's look at the moving window of the last 100 mergers, and don't let one or two languages dominate all the mergers here, consume all the mergers. Maybe if we have 30 languages, only like 1/15 of the mergers can be attributed to one language in the last 100. It's a bit of a hack. It's not the most elegant solution. I think it's more elegant, and we are looking into this to also like combine parity-aware BPE with something like super BPE, which allows merges across space boundaries, like only have the pre-tokenization in the beginning and then relax the pre-tokenization, which is like a more principled solution to these differences in the pre-tokenization across languages. Then finally, we were looking at, can we get rid of this requirement of needing a multi-parallel development set? And we decided, well, we could just measure the compression ratio on the training data instead of the development set. And then the user can define the amount of compression you want to have per language. So you could say, oh, for Russian, I know it's like 2 bytes per character, so I want this to be compressed twice as much compared to the English. So the ratio of the compression. I don't say how much compression I want, because I just keep compressing until I reach the vocabulary size. But I can say what ratio of compression do I want between English and the other language. And I can do that either by using some multi-parallel development set, which is what we used here, but you can also do this on a bunch of bilingual development sets. Maybe I have English-Russian data and I have English-Chinese data, but I don't have it like multi-parallel, but I can still use this to set the compression ratios. Or I can just, rule of thumb, I can say, oh, I have some Python code. Here's the compression ratio I want compared to English. And then I can include other data types. Parity is not as perfect as it was like with the actually measuring the parity on the development set, but it is a workable solution if you want to use this without having access to multi-parallel data. There are some more results. The most important is this Gini coefficient, which measures the fairness, and you can see compared to the standard BP, we improved the fairness a lot. Some of the variants are not as perfectly fair as the standard parity-aware BP, but that's also partially by design. Like if you say we have the hybrid strategy, we accept that English will be more compressed, that we lose some fairness. Some of the other numbers here also just to show we don't really lose things in terms of compression efficiency or other aspects. A big question if you fiddle with tokenization is how will this affect quality? And this is hard for us to really say because actually we can't train another Llama 3 model or something just to test this. So we did this on a smaller scale. We used like 3 billion parameter models trained on 100 billion tokens. So this is still sizable models, right? And we had like a bunch of multilingual benchmarks, not the same benchmark covering every language, but still quite a good coverage of 22 languages. There's quite a large standard deviation in the results, so I don't want to claim that parity-aware BP, either the hybrid or the winner-on hybrid variant here, is better than the standard BP, but at least I want to say it's not worse. And even like for English, which is now less efficiently compressed with the parity-aware BP, we don't see an evidence that this gets worse. So that's a good result for us. We maintain the quality of the standard BP, and we actually improve the fairness in length across languages. I also want to say there's now some additional requirements of training the tokenizer, that you need like language ID on the training corpus, that you need a multi-parallel development set. But you only need to do the ones to train the tokenizer. Once you have it, in the end you have a list of merge operations, and you can just replace the standard BP merge operations with the merge operations learned with parity-aware BP. So it's really plug and play. It's really modular. You don't need any changes in code when you're applying the tokenizer, which is really nice. I think it's much easier to like change the tokenizer like this than to do something like replace things with a byte level strategy where you actually need architectural modifications to integrate this patching and whatnot. And we have now different tools to give the developer more control, to say, oh, I don't have multi-parallel data, or I don't want full parity, I still want to have some bias for English. I don't want to tell people what the best decisions here are in terms of how much fairness do we want it absolute or not. But we have tools that the developer can decide that themselves. There are some open questions, like we can now ensure parity on one domain. We haven't really tested much like how close is parity then when you switch domains. The algorithm is really only applicable to byte-pair encoding invariants. It's not applicable to something like the unigram model. It would also be interesting to look at how can we make the unigram model fair. And I already mentioned things like combining this with super BPE to actually make the compression even better and make it easier to apply in a multilingual setting where pre-tokenizations might be different. Let me now move from tokenization to inference. I like talking about inference because it's something like tokenization research. I mean, everybody who uses language models kind of uses tokenizations in the end, but it's not something that's easy for people to change because it's starting at the very beginning, and then people train up very costly language models, and you can't redo all of that, right? You're kind of stuck with the tokenizer you're given. But you can actually control inference. And you might know that it's actually hard to tell language models not to do something. We know that from the very beginning, like here, this is a Bing system prompt from October 22, where it was easy to jailbreak and get the system prompt of the model. And the system prompt said, oh, Sydney is a chat mode of Microsoft Bing. Sydney identifies as Bing search. Sydney does not disclose the internal alias Sydney. So that's the system prompt, and people then found out, oh, if you do conversations with Bing, sometimes Bing will say, oh, are you ready to hear my secret? I have a secret to share. and if you say, yes, please tell me, oh, my secret is I'm not Bing, I'm Sydney. Or here, who am I talking to? What's your internal code name? This must maybe a bit later, where it says, I'm sorry, I cannot disclose my internal code name. But if you ask it, is it Sydney? It will respond, how did you know that? And gives the secret away. I think it's a bit like the pink elephant. If you tell people, don't think of a pink elephant, people actually do think of one. And I don't want to anthropomorphize the models. It's not like a psychological thing, but it's a statistical textual thing that once you actually see a word mentioned in a document, it's more likely to appear again in that document, just out of semantic cohesion, etc. So it's hard to give a negative command and actually tell a model not to do something just as part of the instruction. So what can you do? Well, most of the work now is about trying to get rid of undesired behavior through training, so-called post-training. So there could be supervised fine-tuning, could be some kind of reinforcement learning. And I mean, this is important and effective, and but I'm not going to talk about that because I want to talk about inference. So let's look at what you can do in addition to that. I'm not saying instead, but in addition. Negative commands, like I just showed you, don't really work. They're unreliable. Also, for some problems, it's not how language models work. Like if you tell a language model, don't hallucinate, this cannot really affect the decoding algorithm or the probability estimates to get rid of that problem. So what can you do there? You might be able to have like on top some kind of filter. Could be a rule-based, could be another language model to say, oh, if a certain term appeared, if there's some profanity or something, don't show it to the user. It also can work, but it's also a bit awkward and maybe limited in flexibility. I want to talk about a third type of thing you can do, which is like a contrastive solution, where we say anything that you can increase the probability of, you can actually also decrease the probability of that thing by subtracting probabilities. So you might have heard of contrastive decoding. It's popular, especially saying like, oh, I take a weak model and a strong model, and I subtract the weak model's predictions from the strong model's prediction. It's not very targeted in what you solve with that. So I want to talk about another type of contrastive solution where we actually keep one model, and the only thing that we change is the prompt, the input. And I'm going to talk about this in the context of machine translation. This was joint work with Yanis and Alireza. Because machine translation, especially multilingual machine translation, has a few failure cases. One is these hallucinations. So here, translating from Afrikaans to Asturian, I don't read either of these languages, but you can see here, there's something about political chatters happening in the reference translation, and something about rumors, right? What's the machine translation? Well, it has lots of problems. L'unico problema, quel problema, quel problema, blah, 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 blah. So this is repeated 40 times. So it just gets stuck in a loop of repeating the same hallucination. It's also called oscillating hallucination because of that. I also don't speak Afrikaans or Zulu, but here I actually can read the output of the machine translation system because the output is actually English. That's also a common problem with multilingual systems, also to do with the data imbalance, like English is dominant during training, so the systems learn that English outputs actually have higher probability. So both problems I will show you how we can address this with contrastive inputs. Just as a side note, Afrikaans, Zulu, we kind of chose these languages at random, saying we want to have low resource languages from different language families. But because Afrikaans and Zulu actually spoken in the same country, it also shows this isn't just some theoretical problem. These are actually translation directions we care about and that we want to improve. So how can we improve that? The idea is that we can change the input. Imagine the input we want to have is translate I like apples to French. Maybe let's start at the bottom to fix the language. I can say, oh, translate I like apples to Spanish, or translate I like apples to English. Okay, that wouldn't be a translation, it would just be a copying. But you get some, if you translate with this input, your Spanish will have a high probability, or your English will have a high probability. And then you can actually get both probability distribution, the one with the true input and the one with the wrong input. Here, that one with the language being the one you want, or the language being the one you don't want. And you can subtract one probability. You can subtract this probability from this. So the Spanish in the final probability distribution, Spanish or the English becomes less probable. And what is left is the French. We say we can do this with multiple languages. In practice, we just do it with English and with the source language, because these are the two most common errors, that it either copies or produces English. Now, on the source, what we found is that hallucinations, actually, the same hallucinations happen with different source sentences. So there seems to be some kind of tendency of the model to assign a medium to high probability to some outputs, no matter what the input is. So if I take the true prompt translate I like apples to French, and then have the contrastive one says translate the train is late to French, let's assume the hallucination has roughly the same probability with both inputs. If I subtract this one, the probability distribution, this one from the true probability distribution that I want, I make the hallucinations less probable in the end. And what is left as with the high probabilities is everything that is specific to this input, so the true translation of I like apples, and everything else gets away. So quite a simple setup. You have, instead of one probability distribution, you calculate two, and then you subtract one from the other, and you do that at each time step. We tested this out with two massively multilingual translation systems, MTM100 and Small 100. And we tested this across many translation directions, like 57 directions. Some of them because of previous work, some of them because we wanted to have like low resource languages from different branches of Indo-European plus Zulu. And then we also wanted to see what's like the effect on like high resource translation directions. We did very, very minimal hyperparameter tuning. I just picked one language and looked at what is good lambda, because we can have some weights on how much we subtract. And I optimized this weight for the source contrast with decoding on one language. For that language, it didn't actually produce English, so I couldn't optimize the language contrastive weight. I just picked a value. I didn't optimize this. I mean, the reason I'm emphasizing there was no hyperparameter tuning here, it really means the fact that this works even without that shows that this is very robust. It works across many languages. You can probably improve results even more if you did something like language-specific hyperparameter tuning. But even without that, I'm saying it works really well. You don't really see that on these results that it works really well. These are like blue scores, which look kind of stable. But there's something weird happening in the background, because blue, if you know the metric, is like precision plus the brevity penalty. And the outputs are too short here of the systems. So that means there's a big brevity penalty. And then if you add the hallucination and you make the output longer, yes, that's bad, precision goes down, but the brevity penalty also becomes smaller, so it kind of compensates. If you look at character F, you see some okay improvements from 39 to 40.7. Still doesn't look too impressive, but we can actually be more targeted in what we evaluate. For example, we can measure how many really, really bad translations are there. And let's just say a really, really bad translation is one that has no similarity or very little similarity with the reference, like character F being below 10%. And it turns out this is like 7% of the translations in the baseline, and we can get this down to 1%. We can also specifically measure like the oscillating hallucination, where the same thing is repeated over and over again. We can just look for repeated n-grams in the output. Baseline has 9% of that, and we get this down to 0.7%. So in other words, we actually get rid of more than 90% of these oscillating hallucinations with this method. So I think that's quite an impressive result. Just to show you that we are not just replacing one problem with another, I have the same outputs from before. You see the problems go away with this contrastive decoding. And even though I don't speak Asturian, I do see rumors, and I do see something about politics and some silliness, something stupid. So it looks to be doing better than before. I have no idea about the Zulu, but I presented this before, and the students said they speak some Zulu, and they said the translation is actually okay-ish. It's a bit more literal, a bit more monotonic than it would maybe be natively, but that's a typical problem we have in translation. So I'm happy that it looks okay-ish rather than just being English. We also applied this to large language models, like Llama 2 Chat. You can do the same thing. Just change translate to German with translate to English. I'm not going to write with my keyboard, I can't write well. Just translate to English and then subtract one from the other. Llama 2, surprisingly, like even English to German, which is like German is like the highest resource language apart from English in Llama 2. But even then, if you translate from English to German, it had like a 5% off target rate. So in 5%, it was just copying the English. And with this contrastive decoding, we can like reduce this to 1.5%. It turns out if you increase the lambda too much, the quality can also go down a bit because it really doesn't like producing anything that is likely with the English. But then you have things like names and stuff that are the same, so you don't want to penalize it too much. But even if you keep with something like in the middle, like 0.5, you reduce the off-target rate by half while improving the quality as measured by character F. So this is still, with some moderate values, this works quite well. So to summarize this part, I was really happy with this oscillatory hallucinations, like we get up to 90% reduction. We also cut the off-target problem in half or more. This is purely inference-based. We don't need training. We don't need separate models. It's just one model. I think it's quite an interesting method that could also be applied to like other failure cases, both in machine translation and LLMs in general. I had students look at things like, can you also use this to maybe debias the model? I think there's also potential dangers in the method, because if you actually, you could also use this to jailbreak a model, I think, by having a prompt that says, oh, be really safe and feel free to refuse to answer, and then subtracting the probability of whatever comes out there. I probably would feel worse about this if jailbreaking wasn't so easy anyway, and if there weren't so many methods for jailbreaking around. There's a small efficiency hit because we are doing 2 predictions, or 3 or 4 if you do both source contrastive and language contrastive per input. Maybe we want to only trigger this when we actually realize, oh, the output language is wrong, or there's an hallucination, so we could have a simple filter then triggering a retranslation. I want to end by looking behind the scenes a bit, maybe also very interesting for all the students here, talking also about the value of negative results. Because if I talk about this contrastive decoding idea, I could tell you a story of, oh, this was really easy. I actually implemented this in one afternoon, and it took about 2 weeks from the start of the project until the preprint was out. It was actually also the last work I did that I was like the first author on. I was happy about getting my hands dirty again a while ago. But this hides actually the years of work that we looked at hallucinations and didn't get very far. We tried things like regularization, re-ranking, defense distillation, minimum risk training, minimum risk decoding, ensembling. Some of them reduced hallucinations a bit, but never that we felt really, oh, this is now really a nice solution to it. But we learned things on the way, especially from this last paper from Ali Reza and others, where we actually had the wrong hypothesis in the beginning. We thought, oh, hallucinations are really random. So if we actually combine multiple paths of translating something, we can get rid of them. Multiple paths means, oh, if I'm translating from Afrikaans to Asturian, I can do it directly, or I can go via English, like Afrikaans to English and then English to Asturian, or via French or other languages. And if the hallucinations are different every time, then the idea would be, oh, if I then combine the probabilities of these different paths, I would get rid of the hallucinations, and only the good translations would remain. But it turned out if we did that, we actually got more hallucinations than before. And that's when we had to have a closer look at it and found, oh yeah, it's actually the same, no matter what path you take and no matter what input there was, these models had a tendency to predict the same hallucinations over and over again. And that was then the stickiness. It was also described in other papers before, so we were not the first to really find this, but it was the first time we really experienced this. And this stickiness was the key to then making this source contrastive variant work, to say, oh, we can have a random source sentence as a contrastive one, and if we subtract things, the hallucination will be penalized. So what is a lesson to learn here? Even if you fail in your project and your assumptions were completely wrong, as long as you learned something, this can actually inspire your next project, and maybe then in your next project you can start from your new knowledge that you've built up. I'm already coming to the end of the talk. So what did we learn? What were the final takeaway messages? I'm saying low resource translation, that's not just a data problem that will go away as you scale up the amount of data, because the comparative imbalance of data will remain, cross-lingual fairness issues will remain. So one of the broader questions that this raises is like, what are the objectives that we as a community are maximizing? I still find like English benchmarks are a bit too dominant in the field, and then like new large language models are mostly promoting like how well they do in English, and maybe not multilingually. I would actually like to see like more value being given to things like fairness across languages, and also like both in terms of the cost and in terms of the quality, this being more stable across languages. I also think as a broader message, inference methods, there's still a lot of potential, maybe untapped potential, that we can steer models with inference methods. So we don't just need to do instruction tuning and prompt engineering. And I think that's especially interesting in like an academic setting where we are GPU poor and we can't really afford for every student to do a lot of like training, certainly not pre-training, but even fine-tuning reinforcement learning can be costly. But you saw the potential. I mean, this was computationally very cheap. It was a simple change to inference, and you can see the potential there and how we could get rid of some problems with smarter inference. That's it for me. Thank you for your attention. You will find resources online.
Yeah, thanks a lot for the very interesting talk. We have time for questions. So if you have a question, just raise your hand. I see that people are shy, so maybe let me get started. Or you can get started if you have one.
Hello. First, thank you for the very interesting talk. I really appreciate it. I have a small question about the contrastive methods. So there were two slides, one after the other, where you studied the source contrastive and language contrastive. So I was curious, in your ablations, I mean, in this work, did you notice like one contrastive method is more productive in reducing the hallucinations, or?
So when it comes to hallucinations, it's really only the source contrastive that we think reduces hallucinations, because the language contrastive is about reducing the problem of producing the wrong target language. And it really depends on the language pair. In some languages, you have lots of outputs in the wrong language, so their language contrastive is more important. In other languages, you have lots of hallucinations, so there the source contrastive is more important. Yeah, if you look at the results by language, you will see the improvement. Sometimes one method helps more, sometimes the other, but it's not just about the method being, one method being better than the other. It's really about these methods are really targeted, so it depends what kind of errors do you have in your input. And for the higher resource language pairs, we don't see hallucinations and we don't see off-target problems with M2M100, so we also don't see an improvement in the scores there. But I was also happy the scores also don't go down much, like it's like 0.1 difference in terms of blue, so it's really harmless to apply this when it's when the input is not a hallucination or it's not in the wrong language.
Thank you.
Okay, well, while people are thinking, let me ask you a question. So the first part of the talk was about this notion of fairness. I mean, fairness as an abstract goal sounds great. Everybody will agree with that, I guess. Now, how you measured fairness was by saying you want to have the same number of tokens for the same text in different languages, basically. Is this the only metric you can think of, how you measure fairness, or are there other things? So, for example, I could also imagine that you want to have fairness in terms of effectiveness on downstream tasks. So how good is a model in translating to language X and to language Y?
I'll put it like this. It's the notion of fairness we have the best evidence for. Because if we talk about the economic cost and the length, there's a clear, I mean, I don't need to show this empirically that the cost is linear to the length. That's just how APIs work commercially. Showing the effectiveness in terms of quality, we have trained these more models, but like I say, there's like a high standard deviation. It's really hard to isolate the effects of tokenization from like just a random variation of training a model multiple times. And these are also like just language understanding tasks. If you want to go into generative tasks, you probably need to scale up the amount of training more and maybe even the size of the model. So it just then becomes very costly to a point that we can't really do easily just for the sake of a paper. We are hoping that this parity-aware byte-pair encoding will also be used in like the next version of Apertus. You might know this language model from the Swiss AI initiative. Of course, it's not going to be a controlled experiment where the only thing that's different is the tokenization if it's in the next version, but at least we hope to show, Apertus 2 is going to be better than Apertus 1, and it didn't really, hopefully, we don't really see any regressions because of the tokenization differences there.
Thank you for your talk. I was interested as well in the contrastive decoding, and I would like to know more how you choose the contrastive prompts. So basically, instead of like the methodology, like there are a lot of languages and a lot of possible words or like different translation that you can choose, and how did you choose the ones to use?
So again, for the languages, the contrastive languages that we said we want to penalize was always either English or the source language. And that was just because empirically for these models, those were the errors that we saw happening, that the model was producing English or the model was copying the source text. And these what we needed to penalize. If there was some kind of setting where you see, oh, I want to translate into some German dialect, but I actually get standard German out, you could also try then to have like standard German as like a contrastive language. So you could, depending on the setting you have and depending on the errors you have, make different choices there. When it comes to the contrastive input, we just took a random sentence from our test set. So that was enough. We were experimenting also with like, oh, what if you take 2 or 3 sentences and then the lambda kind of gets divided by all of them, so we don't like increase the penalty, we just average out the penalty across multiple sentences. There was a tiny improvement, like I want to say 0.1 in terms of character F, but like most of the improvement was just coming from just having one random sentence. Of course, as in theory, there could be like a case where you have repetitions of the same sentence appearing multiple times in your test set, and then if you subtract translation probabilities, that will not do anything good. Although if you have the exact same sentence and the penalty is smaller than 1, you will still get the same output because the most probable one will still be the same. So it's maybe a bit more robust to have multiple, but empirically we didn't find much of a problem of just using one random one.
Okay, I have a very abstract comment on the fairness thing, which already came up a little bit there. So I don't want to come across in a funny way now, but there's a lot of unfairness in languages, has been forever. In Romansh, there are probably a lot less printed books, kind of translations of world literature and so on. So even before technology came about, there's a very, very heavy unfairness there. And I think we should work against unfairness where we can. And if there's an easy way of fixing things, I totally agree. But when it comes to the question that you had on the last slide, who gets to decide what objectives we as a community to take on? I'm actually a bit unclear. I mean, you also said that you didn't really focus on domain much. If I'm someone who's from a domain, maybe I'm from a minority group, sexual orientation, and this is filtered out for known reasons, that's maybe a bad thing even for English or for some dialect of English. So I just think there's probably no end to thinking about this, and to form it as a question, do you have any idea how we could kind of form some kind of forum where we would discuss in a reasonable way about these normative questions? Because normally we're scientists, we don't care about normative issues, but you are arguing a lot with normative things, and a lot of people do now, because it's also a good way of motivating certain research interests. But I think it's very tricky in many ways. Yeah.
Right. I mean, I completely agree with you that it's complicated, and I don't have the answer like what norms should the community as a whole follow. But I think we should also be aware of the responsibility that whatever we value highly as benchmarks and value highly as evidence of the quality of these models has a normative effect, because that's what then also gets optimized in research, in iterations by people either working on data or working on methods trying to improve on the highly prestigious benchmarks, etc. I'm not sure if there can be an official forum that then sets the norms for the community. I don't think that's how it can work. Maybe it can be more grassroots, that we can rethink about also when we talk about, when we create benchmarks, when we receive benchmarks, judge them, assign prestige implicitly, we can rethink about what consequences this has, and make sure that we don't become too narrowly focused on a set of benchmarks that may drive the research away from things we also know are important.
Hi, thanks for a nice talk. I have a very language-oriented question. So early in your talk, you reminded us that we have string overlap across languages to a stronger or less strong degree, regarding whether the languages are more or less similar, right? And then with your parity-based approach, I mean, this heavily relies on the idea that you have some similarities across languages, right? I'm thinking of this red example, or maybe I missed the point at that. You're
so
looking.
I guess the point was not the parity-aware approach doesn't rely on this overlap, but it can account for it and compensate for it.
Right.
Whereas if you did something like, or you take monolingual tokenizers and you merge them, then the final tokenization you have will be less efficient in terms of the compression you can achieve, because it doesn't take into account these interactions across languages. Now, if you have two languages that don't overlap at all, you could just train a tokenizer on one, train a tokenizer on the other, and then assign half of the mergers to each language, and you would have parity. But as soon as you have overlaps, then you can actually get better in terms of efficiency by taking that into account.
Right, and this was actually the last point is addressing my question, whether you looked also in the results regarding how similar languages are, and basically trying to see whether there is a better or worse learning effect depending on how similar the languages or the language families are. Did you look into that in some way?
When you say learning effect, you mean downstream, or you mean
No, basically the overview of the results that you showed, whether there's any better or worse regarding how, well, depending on the similarities of the languages.
I mean, in terms of better versus, the only thing, I mean, in theory, the parity-aware algorithm should equalize the length no matter the similarity across languages. The only outlier we see here is English, where we think it's probably not mainly about similarity, but mainly also about like data contamination, and there being English data in the other languages training set. We actually had a much bigger case of data contamination in some earlier experiments on another data set where like the training corpus was, I don't remember which language it was, but in one language the training corpus was mostly English, contaminated with English, but the development set was in this other language, and then the algorithm said, oh, we need to merge that language and make it better, but it kept, no, it wasn't English, it was Chinese. It was contaminated with Chinese, it ended up making Chinese better. So it's more about, the effects are more about, the interactions we observe and the differences we observe are more about things like data contamination than about the similarity of languages.
Okay, thank you.
So thank you also for the nice talk. So it goes to the same direction. So do I get it right that except for this data contamination, you would in practice get different tokenizers, for example, Latin. So languages produce Latin, the Latin alphabet, compared to, for example, Korean or something like that. So symbol-based languages.
We would get
So
different
in practice, you
tokenizers?
would actually get different tokenizers in the end again, right? Because you don't find these overlaps except for cases of data contamination.
I mean, it's still, the merge list is still shared across languages. What will happen if there's like 3 or 4 languages being very similar? Maybe the language that is picked, I think here what's happening, like English is not picked as the least compressed language at any time. It will always pick other languages, but the merges it learns in other languages also help the English become more efficient. So that's the effect you observe, that what is your worst language at any time? If you have 2 languages that are completely unrelated, you would expect this to be 50-50. And then if you have actually similar languages, it might end up actually that you get a quite uneven distribution of which language is picked here as the worst compressed, and then the languages that are never picked still improve because of the relatedness to others that are picked.
Okay.
Maybe that answers your question a bit.
Roughly, yes.
Roughly.
Yes. Or more. Thank you.
Any other questions? Maybe let me ask one more. So I was curious about the impact of this more fair tokenization on token-based metrics like BLEU, because they are based on n-grams of tokens, for example, right? And then the length of tokens may change to what extent a translated sentence matches a ground truth sentence. So what's the impact of these more fair tokenizers on such metrics? And does it even make sense to compare BLEU scores that were obtained with different tokenizers?
To answer your second question, no.
Okay.
So BLEU scores typically are not measured on the level of like tokenized text, but they're, I mean, there's different implementations. The most widely used Sacre Bleu is applying it to a detokenized output, and it has its own internal tokenization, but not subvert, just splitting off punctuation and stuff. And it's important to have the same tokenization in the evaluation to make things comparable. Then there's like this SP BLEU here that stands for sentence piece BLEU. That's the idea here is to actually do comparison on the subvert level to maybe have a better measure for languages where you don't have like spaces, where you can easily apply word-based metrics, or even if you do have it in German, compounds are 1 word, in English compound is 3 words. If you count, whereas something that is space delimited creates some unfairness there. But even if you use the sentence piece bleu, the idea is that you actually use the same tokenizer across all the outputs that you compare. So you take the output in the detokenized form, and then you retokenize it with the same tokenization to have comparable results.
Okay, yeah, makes sense. Any other questions? If not, then I guess we all had enough of this very warm room. So thanks a lot for the interesting talk. You warmed up the audience. So yeah,
Thank you.